So in this installment, we're going to examine what happens when the torque is not at 90 degrees. And as simpler examples, we've looked at seesaws, and it's very easy to see what's going on. And that's just with a simple lever around a fulcrum. So let's just, again, situate us where we are. We have talked about inertia, momentum, change in momentum, kinetic energy, Newton's second law, basic definition of torque, some other statements of torque. And it's in this case that we are now going to home in on this last part, which is equal to this. The force perpendicular happens to be equal to that RF sine theta. I don't recommend remembering or bothering to use this at all. Fill out your own relationships and you'll be fine. So again, a refresher, we have our unit circle, and we say that this is the direction of positive omega, positive alpha, positive torques. And this is the direction of negative omega, negative alpha, negative torques. So let's consider now, we have a mountain bike wheel. It's fixed to an axle, suspended above the ground. It could be, just a bicycle tire, like on a bicycle where the rear tire is raised off the ground or the front tire is raised off the ground. But the point is that it's free to rotate. It's suspended. And so it has a mass of 1 kilogram. There's a 2 kilogram mass can be attached at different locations to the wheel. So this location, this location, this location. But there's only one mass. I'm just depicting all of those locations. So the question is the torque, how does the torque vary? Does it vary depending on where it's placed? And if so, what is the nature of that displacement? How does it factor in? So let's first connect this to our unit circle. You see these weights are placed like so. And so you can see this is 0 pi over 2 pi, 3 pi over 2, and back to 2 pi. Those are the positions. So now let's first start with 0. So if we were to draw the forces that act on this, it would simply be the weight, which is 20 newtons. The lever arm or fulcrum arm or work arm is like this. And notice they are perpendicular to each other. So this is a simple matter then that the torque is RF. So we have 20 R, whatever the radius is our torque. So that's pretty easy to see. Now let's consider what happens when we are at pi over 2 radians. Here, we have the force of gravity in this direction. Perpendicular is this direction. As you can see, there is no part of the force of gravity that would cause it to go one way or the other. There is no, as in the previous example, the force is perpendicular to the lever arm. Well, here's the lever arm. The force is parallel to it. So there is no torque. So torque is RF. And so we have R this, but F is 0. So the torque is 0. Now, you might argue you could never get it totally balanced perfectly on top, but if you did, it wouldn't go one way or the other. The first one, however, if you put the weight there, you can see it's going to make that wheel rotate in that direction. In fact, it will be a negative torque. So we'll have a negative 20 R. Then we have a 0. Now let's go to pi. This is starting to look a little familiar, perhaps. Your force of gravity, like so. And again, the two are perpendicular to each other. So the torque is R perpendicular times the force, so that's R perpendicular, and in this case, we have 20. But notice now it's a positive 20, so the torque is a positive 20. We had negative 20, torque over here, 0, positive 20. And now let's go to 3 pi over 2. Putting the force on it, force is in this direction, and that's the direction. So if we look at the torque, is R times the perpendicular force. Well, R is what it is, but the perpendicular force is 0. The force is parallel to the lever arm. If you held this wheel in place and put that weight there and released it, it would not do anything. There would be no acceleration because there's no torque on it. So now let's zoom out here a bit and make a graph of this. So we can see when it's 0 degrees, we have minus 20. And that minus 20 is equal to the weight. At pi over 2, we said the torque was 0. And at pi, we said it was positive 20. And at 3 pi over 2, we again said it was 0. And at 2 pi, we're back to the beginning, which is minus 20. And so that is the curve. Now, when we look at this, we might look at this and say, oh, it's looks like a cosine, but it's actually a negative cosine. So in this case here, the torque is related to the negative cosine of theta. And that's why I say it's not a good idea to just rely on this, because in this case, the torque really isn't related to the sine. It's related to the cosine. So we now have mapped this out. Now, a big question we might want to ask ourselves is, what if that mass were placed right there? We know it's not going to be 0, and we know it's not going to be minus 20. It must be somewhere in between, but what is that relationship? What is that relationship? And so if we look at that between 0, say it's about 45 here, we know both sine and cosine of 45 are the same. So how we mathematically come up with what that value is going to require a little bit further study and to do a geometric proof so we could find that, and that's what we will do in the next installment.